Okay, well, thank you very much for inviting me here. It's an honor and also a great pleasure. Today I'll be talking about the statistical theory of clustering, okay? And so clustering, what's that? Well, you have a bunch of points and you want to divide them into groups. And there are basically two contexts in which this arises. Okay, the first context is vector quantization, which is what happens, for example, in audio and video compression. So in audio compression, for example, each data point is a sample from, is a speech sound or a sound sampled from some underlying continuous space. Okay? And you get a few such samples. And the idea is that you want to pick a few representatives that will then serve as a proxy for the entire space. Okay, so future sound samples will be simply replaced by the closest representative. And what matters there is the approximation error or distortion that this induces. Okay? So in this particular setting, in the setting of quantization, it's completely irrelevant whether there are any natural clusters in the data. All you want is a small set of representatives that cover the space nicely. Okay? So the setting that I'll be talking about today is the other setting of clustering, which is a rather different setting. And this is a setting where you're actually looking for natural clusters in the data. Okay, and so returning to a sound example, when a baby is first born, or even when it's in its mother's womb, it's exposed to all these utterances from its mother. And initially, these might seem like they form a continuum. But by the time the baby is about 6 months old, it has quantized these utterances into the phonemes of its mother tongue, okay, into roughly 40 or 50 natural clusters of sounds. Okay, so this is an example of clustering that takes place in a child. Okay, and so this is the sort of clustering that I'll be talking about today. So not quantization, but actually looking for meaningful clusters in data. And this arises in many, many contexts. For example, in exploratory data analysis, where you're trying to just get an initial understanding of a new data set. Or, for example, if a company is trying to partition its customers into natural groups based on their purchase patterns so that it can treat these groups separately. Or if, for example, the clustering is going to be used for subsequent semi-supervised learning, and so on and so forth. Okay, so we'll be talking about sort of natural clusters in data. And so, for example, in this data set, what are the natural clusters? Like, are there 2 clusters or 3 clusters? It's hard to tell, right? Now, there are some criteria out there, actually, like minimal description length, or Bayesian information criterion, Akaike information criterion, that actually return a precise number for the number of clusters. But I think that, one look at this picture should convince you that you should be skeptical about these. Okay, clearly there is no right answer. And so what we'll be looking at today is hierarchical clustering, which finesses this problem altogether. Okay, so a hierarchical clustering lets you have 2 clusters, or 3 clusters, or 4 clusters, any number of clusters that you like. And in many ways, it seems like hierarchical clustering might be more difficult than flat clustering, because you have to find a 2 clustering, and a 3 clustering, and a 4 clustering, and somehow massage them or reconcile them into a tree. But in reality, it can be much easier, because constructing a hierarchy lets you avoid answering some of these questions, like how many clusters are there, that are difficult or perhaps even impossible to answer. Okay? And so that's something that keeps arising in unsupervised learning, how this sort of hierarchical thinking lets you avoid difficult choices in many situations. And we'll see that many times today. Okay? So we'll be talking about hierarchical clustering. And by the way, feel free to stop me at any time if you have any questions. Okay? This should be all quite understandable, I hope. And so what are good hierarchical clustering algorithms? There's a whole bunch of them. One that is one that's very well known is the single linkage algorithm. And this is a very interesting algorithm because it's used both in statistics and in computer science, but for two completely different purposes. In statistics, it's used for clustering. In computer science, it's used for finding the minimum spanning tree of a graph. And there it's usually attributed to Joseph Kruskal, passed away recently. Okay, so this is a very nice, simple algorithm. Let me just quickly remind you of what it is. So you start with a set of points. Let's say there are these 10 points, and then you say that we have 10 individual clusters. Then you merge the two closest clusters. Now you have 9 clusters. So we're going to build this tree bottom up, okay? And then you merge the next two. So we have 8 clusters, and then 7, 6, 5, 4, 3, 2, and now there's 1 cluster. And then going backwards, so you have this 1 clustering. To get a 2 clustering, you break the largest edge. To get a 3 clustering, you break the next largest edge, and so on. Okay, so it's a very nice, simple clustering algorithm. And the question is it a good algorithm? Okay, and so this is a little bit difficult to answer. There are lots of clustering algorithms out there, and it's a little difficult to say which ones are better than the others. And partly in response to this, something that a lot of theoreticians have tried to do is to come up with a set of axioms or properties that any reasonable clustering or that any good clustering should satisfy, and then to see which algorithms actually satisfy these properties. And this was an enterprise that really started in the late 60s and early 70s and was recently picked up again by John Kleinberg in 2001. So what Kleinberg did is that he formulated 3 properties that any good clustering algorithm should satisfy. And then he showed that actually no algorithm satisfies them. Okay, so, but the one that comes closest is single linkage. Okay, now later there were many other people over the past decade who have taken various objections to these properties and formulated other properties. But the one consistent message that comes across throughout all of these is that single linkage is the best one. Okay? Which is weird because in practice single linkage doesn't work well at all. Okay? It has all sorts of very fundamental flaws. And so the question is, what is going on over here? You know, we have all these theoretical analyses that are promoting single linkage as being, you know, the best clustering algorithm or the only one that has, you know, so-and-so desirable properties. And in practice, it can be a bit of a disaster. You know, so what's missing? And I think that one thing that has really been missing from these theoretical analyses is any sort of statistical sense. And when one starts to look at clustering from a statistical viewpoint, then a lot of the flaws of single linkage become apparent. Okay? And so let me say what I mean by that. Okay? So by a statistical view, what I mean is that these points that you're clustering, x1 through xn, these are not arbitrary points, but rather they are draws from some underlying distribution. Okay, so for example, the distribution of a mother's utterances to its child. Okay, now we have no idea what this distribution is, but the mere fact that the points came from a distribution confers all sorts of special properties on them. Okay, and what it means, for example, is that if we were to get another random sample from the same distribution, we would hope to recover roughly the same clustering of the underlying space, at least if the number of points is very large. Okay? Or to put it differently, as the number of points goes to infinity, we would hope that the clusterings we are finding converge to some limit clustering. Okay? So as the number of points grows, we find larger and larger clusterings with more and more points, and we would hope that these converge to some sort of limit clustering, and moreover, we'd like this limit to be something that is meaningful about the underlying distribution. Okay? And so we want a limit, statistical consistency, and we want this limit to be meaningful, to tell us something, to be really informative about the underlying distribution. So all of this talk of consistency seems really obvious and trivial for somebody who's working in classification. And the reason for this is that for classification, we have a very well-developed theory of consistency. and of rates of convergence based, for example, on the VC dimension. But when it comes to clustering, the state of knowledge is much more impoverished. We don't have consistency results for even the most basic settings. Okay, so for example, what is the most popular clustering algorithm in the world? Probably the k-means algorithm. Is it consistent? If you run k-means on n data points and then n plus 1 points and n plus 2 points and go to infinity, does this clustering converge to anything? Well, the only thing that's known is that and this was shown by Pollard in the early 70s, is that the k-means clustering does converge if you always find the global optimum of the k-means cost function. But this is an NP-hard problem, even for k equals 2, okay? But let's say you were able to do that. Let's say you were always able to find the global optimum of k-means. So then it converges, but the thing it converges to is the k-means solution to the underlying distribution. And is that something meaningful? Does the optimizing the k-means cost function on the underlying distribution actually yield clusters that are meaningful in some way? Sometimes maybe, other times it's hard to tell. And so this is kind of, so in all of clustering, there's this really unsatisfactory state of affairs when one starts thinking about it in a statistical way. And from that viewpoint, it turns out that single linkage is actually not too bad. It's actually trying to converge to something meaningful. And let me tell you what it's trying to converge to. Okay? So let's talk about what this limiting object that single linkage is striving towards. Okay? So let's look at this distribution over here, this one with 4 bumps, okay? And I think everybody would agree that it has 4 clusters in it, okay? But where exactly would we draw the boundaries of these clusters? Should we say that this thing over here is a cluster, or should we draw the boundary a little bit further out, or should we draw a boundary a little bit further out? The good thing is we're doing hierarchical clustering, so we can say that all of these are clusters. We don't have to make these choices, okay? And so this gives us a very nice notion of what the limiting object is. What we say is that take any level set of the density, so take any density level lambda, and just cut off the distribution at the portion that's above lambda. And then look at those connected components. We're going to just call them clusters, okay? And because you're allowed to vary lambda, you get infinitely many clusters, and they form a tree, okay? And this is the cluster tree, and it turns out that single linkage is trying to get at this thing, okay? And let's see, so let's just look at this in a little bit more detail, okay? So here's an example of a density in 1 dimension, and what the cluster tree does is that you take a density level, and you look at the connected components above that level. So, for example, if we look at level lambda 1, then there's only 1 cluster at that level, which is this interval over here. Okay, if we look at density level lambda 2, then we cut at this line, and we get 2 clusters, this one and this one over here. If we look at lambda 3, then we get 3 clusters, this one and this one. And these clusters form a hierarchy because they are nested. Any 2 clusters are either disjoint, or one is contained within the other. So lambda has infinitely many values. We get this infinite tree, and single linkage apparently is trying to find this tree. Okay, and let's see how that might happen. So let's say we sample 6 points from the underlying distribution, from this density, okay? And now we apply single linkage to these points. So first it merges the 2 closest points, and we can think of this cluster as being a proxy for this underlying cluster, this one over here. And then it merges the next 2 closest points, and we can think of that as being a proxy for this cluster over here. And then the next 2, and we can think that that's a approximation of this cluster, and so on, okay? And so, okay, and then this last one is an approximation either for this cluster or maybe for the whole support, okay? And so in this way, oh, what are these vertices? So this is the tree that's finally constructed by single linkage, okay? So the first 2 points that it merges are points 2 and 3. So, because it's a bottom-up process, okay? And any interior node of the tree is considered a cluster, okay? The cluster of its descendant leaves, okay? And so it really seems like like the single linkage procedure is somehow consistent with the cluster tree, but we need a formal definition of this. And this was one of the things that the great statistician Hardigan did in the mid-70s. So he came up with a notion of consistency for clustering based on this limiting object, this infinite tree. Okay? And so this is his notion. This is Hardigan's notion of consistency. He says, let's look at any density level, lambda, and let's look at two connected components at this level. So for example, this connected component and this connected component. So those are two clusters. Okay? Now take a finite data set and construct a tree, build a finite tree from that data set. And look at the points in that finite set that fall here and the points in the finite set that fall there. They should end up in different clusters of the tree. Okay? So in other words, there should be some subtree that contains all the points in here and a disjoint subtree that contains all the points in here. And in fact, that doesn't have to hold for any particular n. It just has to hold as n goes to infinity. Okay? And that's the notion of consistency. So it's a notion of separation. Look at any two clusters that are disjoint, draw a finite data set, look at the points that fall here, the points that fall here. These points should end up in different subtrees of the final hierarchy. And as long as that occurs in the limit, we say that this clustering procedure is Hardigan consistent. Okay? So this was his notion of consistency for clustering. And what he showed is that single linkage is actually consistent in one dimension. And this is one of the few, or this has been one of the few decent results in the statistical theory of clustering. Okay? Here we have an algorithm that's a reasonable, simple algorithm, and it's actually consistent, and the thing it's converging to is actually something sensible. Okay? This is wonderful. Okay? This is great news. And so naturally, what he wanted to do next was to then look at higher dimension. Okay, so he said, okay, we've done consistency for d equals 1. Let's do d equals 2, d equals 3, and so on. And unfortunately, what he found is that as soon as you move to 2 dimensions, its single linkage ceases to be consistent. Okay? It's not consistent in any dimension greater than 1. And he does this by a lovely reduction to continuum percolation. And we'll talk a little bit about percolation later on. Okay? But what is the problem? You know, why is single linkage not consistent when the dimension goes up? So, you know, the sort of bad situation is something like this, where you have these two clusters that are high-density clusters separated by a low-density region. And for consistency, what we need is that single linkage should not connect the two clusters until each of the clusters is individually fully connected. Okay, so the clusters have to individually be connected before a bridge is built between them. But when the dimension is greater than 1, it's very easy to fall into this situation where you have 2 points that are in the different clusters that are relatively close together, and that connection ends up being made. And it turns out that, in fact, it's inevitable. Okay? And so this was really bad news, and so Hardigan left it as an open problem to try and come up with a method that's consistent in dimension greater than 1. And so that's one of the things that we were able to show a few years ago. And we found that actually you just need to make a very small change to single linkage. So it's a nice algorithm, and you just need to tweak it a little bit, and all of a sudden it becomes consistent in any dimension. And what's more, not only is it consistent, you can give good finite sample rates of convergence. And it turns out that these rates of convergence are optimal in a min-max sense that I'll talk about later. Okay? Okay, and so what is this change that you have to make to single linkage? And to tell you about that, it's a very small change, but to understand it, we just have to look at single linkage from a slightly different viewpoint by thinking of it in terms of nearest neighbor graphs. Okay, so I've described single linkage in a particular way, the way it's usually presented in textbooks, but now we'll take a somewhat different look at single linkage in terms of nearest neighbor graphs. Okay, so what are these near neighbor graphs? Well, these have been all the rage in machine learning for the past 2 decades or so. And basically, they are graphs that capture the local structure of a data set. Okay, so you start with some data set that is super complicated and unfathomable. And from it, you extract this graph, this nice abstract mathematical object. And the way you do that is that you create a node for each data point, and then you connect 2 nodes with an edge, with an undirected edge, if those 2 points are close together according to some precise criterion. Okay, so you start with this kind of chaotic looking data set like this, and you get a nice graph. And then once you've constructed this graph, it gets used for a wide range of different purposes. For example, for clustering the data by finding cuts in the graph, or for doing semi-supervised learning, where you have labels for some of the points. You say, oh, this is a plus, that's a minus, that's a plus. And then you propagate the labels along the edges of the graph to obtain labels for everything. Or for things like embedding and manifold learning, where you first construct this graph, and then you look for an embedding of these points that preserves the neighborhood structure of the graph. Okay? And so these graphs have many purposes. And so how exactly do you build these graphs? Well, there are sort of 2 very popular ways of building the graphs. The first is, so the only thing is, so there's going to be a node for each point. The question is, what is the criterion for putting in edges? And so one popular way of doing it is to connect any 2 nodes whose corresponding points are within a distance r of each other. Okay? And that's called an R graph. And the other is simply to connect each point to its k nearest neighbors. Okay? Now, the reason why there are 2 criteria instead of just 1 is that neither of them is entirely satisfactory. And so it boils down to choosing the lesser of the 2 evils in, whatever situation you actually find yourself in. Okay, so both of these have significant failure modes. The problem with the first one, the problem with connecting nodes at a specific distance r, is that it is not sensitive to multi-scale structure in the data. Okay, so for example, let's say you have data like this, where you have 3 clusters, but they're all at very different scales. So if the value r you choose is large, then this cluster will be correctly captured, but these 2 might get combined into 1. If the r you choose is very small, well, then you'll correctly capture this cluster and maybe this, but you might have no edges at all inside this cluster. Okay? And so there's this problem of scale when you have a specific value of r. Now, these situations are not pathological. Having multiple scales is not some sort of anomaly or pathology. Even a very easy data set like the handwritten digits data set that I think everybody's familiar with. So the handwritten digit data set has got 10 natural clusters, the zeros, the ones, the twos, and so on. And the cluster of ones has a very small radius because there's very little variation in ones, whereas the cluster of zeros has much larger radius. So even very easy data sets like that have this sort of wide range of scales. Okay? And so this is a very real problem. Now, the second method was meant to address this problem. So you connect points to their k nearest neighbors. And so it would probably do the right thing over here. So points here would get connected to the k nearest neighbors. So it would adapt to the scale of this cluster. Points here would get connected to k nearest neighbors. And in this situation, the k nearest neighbors would probably be within the same cluster. And so it would adapt nicely. The bad case arises when you happen to have an outlier, which again is not an anomaly at all. Okay, but when you have an outlier like this, then it gets connected to its k nearest neighbors, and then all hell could break loose. Okay, at that point, you get these spurious connections. Okay, so the basic problem, however, is that when data has multi-scale structure, it's very hard to condense it to a flat graph. That's just an inherent problem. And this problem would go away if we simply taught hierarchically. Instead of just trying to construct one flat graph, what about constructing a whole hierarchy of graphs at different scales? This problem would vanish. And in fact, that's what single linkage is implicitly doing. And so we'll view single linkage in that way. Okay, so this is another view of the single linkage algorithm. You can think of this algorithm as having a knob that starts at 0 and you slowly turn the knob until it reaches infinity. Okay? So you're turning this knob, and when it reaches R, you connect all points that are within distance R of each other. If there's a point that's not connected, you throw it away, and you just output the connected components. Those are the clusters at scale R. Then you turn it some more, you get a higher value of R, you get slightly larger clusters, and so on. This is what single linkage is doing. Okay? So this is another way of writing out the single linkage algorithm. So what happens is essentially, so there's this knob that's being turned, and initially none of the data points is active. A point jumps into existence only when the knob reaches the R, which is the distance from that point to its nearest neighbor. So a point comes into existence when the knob reaches R of xi, which is the distance from xi to its nearest neighbor. And once it comes into existence, it's always part of the graph. Okay? And when you get to R, you connect everything at distance R, and you output the components, and you keep going. Okay? Now, it seems like there are infinitely many values of R, but actually, if there are n points, then there are only n choose 2 different edge lengths, and so it's actually a finite process. Okay? So this is the single linkage algorithm, and we are going to change this algorithm because this is not consistent. And it turns out the changes you have to make are minuscule. So this is the original algorithm, and this is the modified algorithm. We've literally just changed like 4 characters in the algorithm. Okay? So what are these changes? So the first change is that you delay the appearance of a node. Okay, so initially, a node springs into existence when the knob reaches the distance from that node to its nearest neighbor. Now, you delay the appearance of the node. It springs into existence when the knob reaches the distance from that node to its kth nearest neighbor. This makes everything more robust. Okay, that's the first change. The second change is that when you're at scale R, when you reach R, instead of connecting everything that's within distance R of each other, you give yourself a little bit more slack. You connect everything that's at distance alpha R from each other. And the alpha we'll be using is the square root of 2. And it turns out that if you make this change, if you make these 2 changes, then all of a sudden, single linkage becomes consistent in any dimension. Okay? So this is what you need to make single linkage consistent. Now, consistency is an asymptotic property, which means that you need infinite amounts of data. And so, of course, in real life, we are much more concerned with what you can do with a finite amount of data. So what would happen over here? So what we are saying is that as the amount of data goes to infinity, you're eventually going to identify every cluster. But clearly, if there's some cluster that really stands out, that is very salient, then you should be able to identify it using much less data. Okay? And so that's the kind of finite sample result we want to give. We want to say that there's a notion of cluster salience, such that if a cluster is salient, we'll pick it out really early on. Okay? And so how do you define cluster salience? It seems like it's something complicated. But it turns out that it's actually really simple to do, because there are only 2 effects that you have to pick out, that you have to worry about. Okay, and so let me tell you what these effects are. Okay, and then we'll use these to define what it means for a cluster to be prominent or salient. The first effect is the thin bridge. Okay, so imagine that you have a cluster that looks like this, which is a dumbbell. Then in a finite data set, you'll probably get some points on the left, and you'll get some points on the right, but they will look disconnected, okay? Because even though there's a high density region in the middle, it's so thin that you don't get points in there. And so you need a lot of data points in order to realize that this is all just one cluster. Now, the way that we're going to deal with this is we're going to be talking about a buffer zone around each cluster. So for any set Z, which will typically be a cluster, and for any real number sigma, like sigma equal to 0.1, what we'll say is we'll say that Z of sigma is everything within distance sigma of Z. Okay, so it's like Z, this is the Minkowski sum of Z and a ball of radius sigma. Okay, so that's what Z of sigma is, like a buffer zone around. So that's the first effect. And the second effect we have to worry about is this one, where you have these two densities and they both have these two clusters over here, but here there's a much bigger dip than in this one. And so intuitively it seems like this, separating these two clusters will be a lot easier than separating these two. Okay? And that's it. These are the only two effects that we need to capture. Okay? And so now we have a notion of cluster salience or separation. So let A and A prime be any two clusters. We're not going to make any assumptions about the underlying distribution. It doesn't have to be Lipschitz or anything like that, okay? Which means that the clusters could look pretty weird, okay? So let's say you have these two clusters. Their shapes could be anything. What we will say is that these clusters are sigma epsilon separated if the following property holds. First of all, they have to be separated. So there's some set S that separates the two of them. If you want to go from one cluster to the other, you have to cross S. Okay? And second, the density of this separator set is less than the density, the maximum density in the separator set is less than the minimum density in either of these two clusters, even if you put a buffer zone around all of them. Okay? So if we have a buffer zone of radius sigma around the separator set and around each of the clusters, the density in this middle region, anywhere in this middle region, is less than the minimum density in this region and the minimum density in this region. Okay? So the main thing to observe over here is that if you have two disjoint clusters, they will definitely be sigma epsilon separated for some sigma and epsilon small enough. Okay, so you will always have sigma epsilon separation. But if sigma and epsilon are large, then it will be very easy to separate these two clusters. And just with a small amount of data, this modified single linkage procedure will do it. Okay? And so this is the notion of separation. And so here's what we show. We show this, this result that holds uniformly over all clusters. So for any two connected sets A and A prime, we know that for any two of these clusters, A and A prime, which are connected components of the density at some level, we know that they are going to be sigma epsilon separated for some sigma and some epsilon greater than 0. And it turns out that if the number of data points exceeds this value over here, then they will be separated by this modified single linkage procedure, in the sense that there will be one subtree of the return tree that contains all the points in A, and a disjoint subtree that contains all the points in A prime. Okay, so they will get separated by the procedure. Or to put it differently, there's an intermediate graph. If we think of this procedure as generating a hierarchy of graphs, there's some intermediate graph in which A and A prime are each individually connected, but they lie in separate connected components of the graph. Okay? And we'll also see that this is near optimal in some sense. Okay? Okay, so this is kind of an interesting situation. So, single linkage is not consistent, and then you like tweak something very small in it, and it becomes consistent and gives nice rates of convergence. So why is that? What is the argument? And basically, it's an exercise in percolation. Okay, and so let's just go through the argument carefully. Okay, so I'll just make a high-level point first, which is just about these kind of percolation arguments. Okay, so in computer science, at least, the sort of random graphs that we see a lot are Erdős-Renyi random graphs, where you have n nodes, and for each pair of nodes, you flip a coin with probability p, and you put an edge there if the coin turns out to be heads, okay? And these graphs have been analyzed a lot. But these are not the sort of graphs that arise in the statistical context that I'm talking about, where we're much more interested in what would be called random geometric graphs, okay? So here, you get points sampled from some underlying distribution, and then you put edges between points according to a deterministic criterion. So in Erdos-Renyi graphs, the randomness is in the edges. So the amount of entropy is n squared. Whereas in random geometric graphs, the randomness is in the nodes. So the entropy is much less. The amount of entropy is proportional to n. And in both cases, we're very much interested in these sort of percolation questions. So at what stage, in Erdos-Renyi random graphs, for example, as you grow p, at what stage do you get a giant component? You get a single connected component that contains almost all of the points. And what we need to do is to do a similar sort of analysis, but for random geometric graphs. Okay, so let's see so let's go through the analysis now. And this is the algorithm we have over here. This is the algorithm we're analyzing. And single linkage just has k equals 1. Okay? So the hope of single linkage is that the first 2 points that get connected will lie in the region of highest density. Okay? That the first pair of points to get connected are going to lie right over here in the region of highest density. And that could happen, but due to sampling error, it might not happen. Okay? It's quite possible that the first 2 points that get connected would lie in here, or maybe even in here. Okay? So we have to control for sampling error. And the way we'll do that is by simply using very simple VC dimension bounds. Okay? And so using VC dimension, we can get uniform bounds for the number of points that lie in any ball in space. And these are very useful. Okay? So what the VC dimension will tell us is that for every single ball in RD, even though there are infinitely many such balls, the number of points that fall in the ball is going to be its expected value. So you have n data points. The probability mass of the ball is f of b. So the expected number of points is n times f of b. And then the error bar is this thing over here. Okay? And so in particular, if you're just looking for balls containing 1 point, which is what would happen if you were just looking at the nearest neighbor, then n times f of b would be 1. Okay? Because we're looking for balls just containing 1 point. And the error bar would totally dominate that. Okay? So we need to look for balls that contain enough points that this error bar is of the same order of magnitude as the number of points. And what this tells you is that the number of points you should be looking for is roughly d log n. And so that's why we're just going to set k to d log n. Okay? So just so that we can apply these uniform convergence results. Okay? And so for robustness, we're just going to say, look for the closest, look for the kth closest point where k is d log n. And now we can be sure that for any ball that we're looking at, because it contains this many points, the number of points in that ball is really a good reflection of the density, of the probability mass of that ball. Okay. Okay, so now let's go through the argument. Okay, so let's look at any two sets, A and A prime, that are, oh, and I should say that that's the only statistical part of the analysis. And this is why we get a uniform convergence over all pairs. Okay, we don't need anything else. We just need every ball to be okay. Oh, and there's one other thing that we'll see in a second. Okay, so now let's look at two clusters, A and A prime, and let's say they're separated. So this satisfies this picture. Each of the two clusters has some density at least lambda, and that includes this little buffer zone around it. And meanwhile, the separator set has density less than lambda, lambda times 1 minus epsilon. And again, that includes the buffer zone around that. Okay? So the first thing we need to show, so we're going to be turning this knob, but the first thing we'll show is that you get to a point where every node in A and the buffer zone around it is active. Okay, it's been activated. Every node in A prime and the buffer zone around it has been activated. And there's no connection between A and A prime. There's no path from A to A prime using edges of length alpha r. Okay? Okay. So why is that? Well, this just follows directly from the kind of density estimates that we've been using. Okay? So there's going to be a point of time in which we're going to get to a value of R where every node in A has got at least k points within distance R, okay? And every node in A prime has at least k points within distance R, so these are activated. And no node in the middle region has got k points within distance R, okay? And this is because we have this separation, lambda and lambda times 1 minus epsilon. So no point in the middle has got k points within distance R. So the graph at that level contains every point in here, and no point in the middle. And the buffer zone in the middle is so wide that an edge cannot cross it, okay? Because we're only allowing edges of R square root 2. No edge can cross that middle zone. And so therefore, these two sets are separated. So this is the easy part of the argument. The slightly more complicated part of the argument is that we have to show that at that value of R, although this is separated from this cluster is internally connected, okay? And so that's sort of the percolation part of the argument. We have to show that the cluster is internally connected. And so how do we do that, okay? So, so we know that we're at a scale at which any data point in here is activated. It's part of that graph G sub R. And so is any data point in this buffer zone around it. So all of these black points are in the graph. But we have to show that any two of them are connected, that there is some set sequence of edges that leads from one to the other. Now the worst case is something like this, where the cluster is just super thin. It's just like a line, okay? And so there we are really relying upon the buffer zone. And to show connectivity now, we really want lots of edges, okay? And this is where alpha is helping us, right? So we said that instead of just connecting things that are within distance R, we're going to connect things that are within distance R times square root 2. So we're going to connect more stuff. And we need, and this is something that helps with showing connectivity. So it's very easy to show that if alpha equals 2, these clusters are going to be connected. And we were able to do this for alpha equal to square root of 2. And it's an open problem to do it for alpha equals 1, which I think should be the case, okay? But we weren't able to do that. So the larger you make alpha, the easier it is to show connectivity, but you get a worse rate of convergence, okay? And so we were able to bring it down from alpha equal to 2 to square root 2, but it would be nice to go down further.
But if you are increasing the alpha, aren't you losing the separation then?
Yeah, so you have to scale the separation up. And so what it boils down to is that you get the alpha basically ends up showing up in the convergence rate. Like the number of points you need grows by that alpha to the dimension. Okay, and so that's right. Great. So how do we show connectedness? So here's the argument. Okay, so these are 2 points. Let's look at 2 points, x and x prime, that are in the same cluster. And that means that there is some path between them in the cluster, okay? And we also have the buffer zone around it. So to show that x is connected to x prime, we have to exhibit a set of data points, x1, x2, x3, x4, x5, x6, x7, x8, that connect the two, okay? So that there's, all these data points are active in the graph, that they exist in the graph, and the first data point is x, and the last one is x prime, and any consecutive pair of points is within distance alpha r of each other. So this is what we need to do to show connectivity, okay? So the first thing to note is that we will just look at data points that lie within distance r of this path. And therefore, they lie within the buffer zone around the cluster. So all the points are active. We don't have to worry about the points not being active in the graph, okay? We just have to show that there are enough points that we get a full path from x to x prime, okay? And the way we'll do that is that we'll just move along the path, okay? And let's say that we've got to xi so far, okay? So we're at xi. It's within distance r of the path. So let's draw a ball of radius r around xi. And look at the furthest point along the path that ball touches, okay? And now so that's that point over there. And now let's put a ball of radius r around that point. So xi is on the surface of that ball. And now let's look at the half ball that's, for which this half space is orthogonal to this vector over here. Okay, so at right angles to xi in this thing. Okay, so let's look at this half ball. So this is the other place where we need a VC guarantee. So previously, we looked at uniform convergence over balls. We also need uniform convergence over half balls. That's what I haven't mentioned, okay? So over these hemiballs or hemispheres, okay? Now, we have enough points that there are going to be some data points in here. So pick any of them. Because the radius of this ball is r, the distance between these two is at most r times the square root of 2. And moreover, by continuity, we know that if we were to draw a ball around this one, it would move a little further along the path. And so we have made progress. We have moved closer to the goal. Okay? And the number of data points is finite, so this process will end after a finite number of steps. And in this way, we get a path from x to x prime. Okay? And so that's how we establish connectivity. And the open problem, I would say, is to do it for alpha equal to 1. That would be interesting if we could manage that. Okay. So, so I said that there is a lower bound that's almost matching. I won't go into the construction of it. I'll just say, what one uses. And basically, the thing one uses, is Fano's inequality, which I'm just going to mention because I really love this thing. Okay, it's so powerful. It's this method from information theory that really provides lower bounds for a lot of statistical estimation problems. Okay. And it's usually phrased as a game between a player and Mother Nature, okay? And what happens is that the player and nature agree beforehand on a set of distributions, okay? So theta 1 to theta L. So they agree beforehand on these distributions, and then nature secretly chooses one of these distributions and doesn't say which one it is, okay? So nature chooses some distribution. The player gets to see n samples from this distribution and then has to guess what the distribution is. Okay, and so what Fano's inequality tells you is how many samples does that player have to see in order to be able to guess the distribution with probability at least a half. And it turns out that the number of samples is at least the following. Log the number of different distributions divided by twice the average KL divergence between those distributions. So if the distributions are really close together, then you need more samples, okay? And so, with tools like this, it's very easy to construct lower bounds, and then you can show that those various terms that appeared are close to optimal. Okay. So let me talk about some, let me just briefly mention some. So this is a result of ours from 2010, and since then there's been a bunch of interesting other work on this problem. And so let me just briefly mention what it is. Okay, the first is a different cluster tree estimator. So this is what we had for the cluster tree. And then Samori Patufe and Ule von Luxburg showed that something similar holds, where instead of the R graph, where you connect everything at distance R, you use a nearest neighbor graph, where you connect everything at distance R, but you connect only the k closest things, something like that. So it's potentially a sparser graph, and they show that similar rates of convergence hold for this. And in fact, there's a whole host of graphs between the R graph and the k nearest neighbor graph for which this holds. Okay, and this is something that we try to work out later. Okay. The second thing that people have been looking at is this notion of Hardigan consistency. It's it's a really nice notion, and it really took a lot of insight to come up with this. But is it strong enough? Okay. Or should we really have a stronger criterion? Now that we've achieved this, maybe we need a stronger criterion for consistency. And it turns out that this notion of consistency allows certain allows a certain amount of fragmentation. Okay, so let's say that this is the underlying density. This notion of consistency, and let's say you get points 1, 2, 3, 4 from the left, and 5, 6, 7, 8 from the right. Okay, we'd like a cluster tree something like this. But Hardigan consistency allows you to create spurious clusters on the left or on the right. Okay? So all the notion of consistency is saying, all that Hardigan consistency says, is that if you have two clusters that are separate, they have to end up in different subtrees. But it doesn't say that that you will not find clusters that don't exist in the underlying density. Okay, so it does not guard against excessive fragmentation. And so one of the things that we were looking at is a very simple way to prune the tree that gets rid of this kind of problem. Okay? And more recently, there have been other attempts at formalizing stronger notions than Hardigan consistency, for example, by Belkin, Justin Eldridge, and Yusu Wang. Okay? So what are some open problems? One open problem is, one of the nice things about this kind of consistency is that the limiting object is something reasonable. The cluster tree really seems like it contains valuable cluster information from the underlying density. But is this the only reasonable limiting object? Hopefully not. Hopefully there are other hierarchies that one can define on the underlying distribution that are also reasonable. But what are these? It would be really nice to have some alternative limiting objects that are clearly meaningful. Okay? The second is that this notion is really, this kind of cluster tree is really for densities. And what happens with discrete distributions? Okay, and the final question, which is a practical question, is that hierarchical clustering is really extremely useful. And the major hurdle to using it in practice is simply that it's quadratic. Okay? If it were faster, so we could actually run it on data sets of, say 100,000 points, a lot more people would be using it, instead of, say, k-means. And so is there a way to do this, to achieve this kind of Hardigan consistency by a procedure that runs in just n log n time? The procedure I've shown is a variant of single linkage and therefore has roughly the same running time as that. Okay? So finally, I'd just like to thank my co-authors, Kamalika Chaudhary, Samori Potufe, and Levan Luxburg. Okay, thank you.